Thank you, Alice. So yes, this is a talk about a recent paper, a joint work with Ronald Kramer, Chris, and Oded. So it's about solving this problem. So we're given an ideal with a promised principle, and we're trying to recover a short of the generator. So why are we interested in this? Why? I mean, if you're an algebraist, you might just be interested for the sake of it. But in our case, we are interested to this problem because basically it's a way to break certain crypto system. So you know that a lot of recent schemes are based on what we call ideal lattices, but those are not really ideals. Typically, they're more modules of a ring. So that's how we build the problems like ring cis, ring LWE. But in some very special cases, some crypto systems have been built really on ideals, meaning that the public key of those crypto systems is going to be an ideal which is given by a Z basis of that ideal. And on the other hand, the party who has a secret key, well, the secret key for him is a generator of that principal ideal. And typically it's going to be a short generator so that he can solve some geometric problem better than other people can. And so the crypto system I'm thinking of are in particular fully homomorphic encryption. So for the fully homomorphic encryption, it was more accidental because little by little we got rid of this framework and we were able to build those fully homomorphic encryption out of the true ring LWE assumption. But for multilinear maps, we are not there yet. For multilinear maps, we're currently stuck with using those ideals unless you go to the integer ones. But well, there's also there's also the graph-induced one where we get out of this framework as well. Okay, maybe those ones are the most efficient one. I don't know exactly. Okay, but if we try to break those, basically our goal is to recover the secret key from the public key. So given an ideal or given a basis of it, we want to recover not only a generator of it, but we want to recover a short generator of it. So the first problem that we're going to solve this in two parts. First, we're going to just recover a generator of it, which maybe, as you know, is actually not that an easy of a task. So it's called the principal ideal problem. But this generator might not even be short, so it might not be a useful generator to break the crypto system. It might not be the secret key. And then once we have this arbitrary generator, well, we're going to then try to recover the short one. So there might be several equivalently short ones, and we don't really mind which one we get, but we want to recover something that's basically equivalently short as the one that has been chosen as a secret. All right. So what is the cost of those two steps? So it's only for quite a while. The first problem was thought to be exponential time, but really the reason it was exponential time is because mathematicians never really studied the large dimension cases until very recently. Bias and Ficker tried to adapt the algorithm for the principal ideal problem in small dimension. They adapted it to large dimension and they obtained a sub-exponential algorithm. So basically it's a matter of balancing lattice reduction step with a factoring step. And if you balance everything properly, you get this sub-exponential over time. More interestingly, if you care about quantum algorithm, it's seen that this problem should be easy for a quantum algorithm. So I'm being careful with this statement because only the first paper has been published yet, but it's solved another problem. It solved the unit problem. Oh, I'm sorry. So I don't remember the four authors of the first one. So I just find sorry. Thank you very much. The second is Bias and Song, and the third one is Campbell Shepard, yes. So Yes, so it seems that in a short time, in a short amount of time, we should get a serious quantum polynomial time algorithm for this problem. Pardon? Isn't that supposed to be secret? No, not. No, maybe I'm used to crypto conference. But yes, yes. So there's. Okay, well, we'll get there. I mean, it's believable that we get there. But let's move to our point. So the study of this work is more the second problem. So now I've been given a short generator, sorry, an arbitrary one, and the goal is to recover a short one. So this can be framed as actually a lattice problem, so a CVP problem, the closest vector problem, in the lattice that we can call the log unit lattice, or I'll detail what it is later. But actually, for the crypto system we have in mind, so in the worst case, it might be a closed vector problem. But for the crypto system we have in mind, it actually transforms to a bounded distance decoding problem, meaning that we have to solve the closed vector problem with the promise that the point is relatively close to the lattice. So that's supposedly an easier problem, but unless you have a huge gap between the volume and the distance to the root volume and the distance to the lattice, it's not that easy of a problem. It was surprising that this Solidoki paper, in this paper, they claim that in fact, in the case where we choose a cyclotomic ring for a power of 2 as a conductor, this one is actually easy. So they don't provide a proof of it, but apparently it's quite easy to confirm this experimentally. So it's a bit frustrating because apparently it works in practice, but we don't really know why and if it scales. So that's what we study in this work. We focus on the second step, and we try to analyze this approach, and we indeed prove that it can be solved in classical polynomial time for those instances, and we generalize it a little bit. We're not restricted to powers of 2 cyclotomic, but we can deal with powers of any prime for the conductor of the cyclotomic number. All right, so let me move to the preliminaries. So we need to start with this log unit lattice. So what it is. So there's this quite magic tool, the logarithmic embedding. Essentially, you take a number field, so it has a degree n, and we're going to assume that all its embeddings are complex. So we have sigma embeddings to the complex numbers, and we take R to be its string of integers. And the logarithmic embedding is defined very simply. We're going to associate to a point of our number field the logarithm of the absolute value of each of those embeddings. And so because embeddings are multiplicative morphism, and because absolute values are also preserve multiplication, essentially when we take this logarithmic embedding, we get a morphism from the multiplicative group of K to the vector space Rn. And now, if we restrict it, this logarithmic embedding not to the whole field but to its ring of integer, well then we still get something that's preserved multiplication, but it's only a morphism of monoid because now multiplication on this ring is just a monoid. All right, and that's where the unit group trait kicks in. So basically, it's this monoid R. There is a group hidden instead of it. The unit of this ring forms a group. So if we apply the logarithmic embedding to this restricted set, to only the units, well, we should again get a group. Okay, and this group, not only it's a group, but it's also a lattice. So that's what we're going to call the log unit lattice, lambda. And Dirichlet unit theorems tells you quite some information about this lattice. So it's going to tell you the rank of that lattice, which you can compute essentially if you just know the number of real embeddings and the number of complex embeddings. And also, this theorem tells you that when you take the log, you don't lose a lot of information. Basically, the kernel of this morphism is quite small. It's just the set of cyclic roots of the unity. So if you remember our goal, we were looking for a generator or something of the same size. So it means that if we go to the log embedding, the only information we lose is a multiplication by a root of unity. So basically, moving to the log embedding means that we don't really lose information. And that's why we can essentially reduce our problem to a CVP in that lattice, to a closest vector problem in that lattice. So we have some generator H of an ideal, and it's not short, but we're looking for G that's going to be a short one. And we know that if G and H should generate the same ideal, then they differ multiplicatively only by a unit. So we have H, which is G times U for some U, okay? And we have H, and we're trying to recover G. And if we take the log of this whole equation, well, we know that the log of U lies in this lattice lambda. So basically, we're looking for G such that the log of G belongs to this coset of the log unit lattice. So then there's a little bit of a jump here to do, and then we want to say that actually G is going to be the smallest of all those representative if log of U is the closest vector to log of H. So for this, it's not exactly obvious because we have essentially to believe that the function log preserves the notion of smallness and closeness. So it's in general, if you're looking at one norm on one side and another norm on the other side, it's not obvious which one corresponds to which one. But actually, as I told you, in the instance we're interested in, we're not trying to solve the CVP problem, not looking for the closest vector problem, but we have the promise that it is somehow close to the lattice. And just this promise will make this issue of choosing what we mean by small and close kind of disappear. We can just work with the nice norms, the nice L2 norms that we all love. All right, so because it's early in the morning, let's do a little bit of a gymnastic on those algebraic notions. So here I'm taking a simple two-dimensional example. I'm taking the ring of integer of Q adjointed with the square root of Q adjoined with the square root of 2. And so there are two embeddings for this number field. So on the x-axis I've put basically the natural one, and then the conjugate of it. So the point 1 of our number field is going to lie here, okay? And then all the multiples, all the z multiples of 1 are going to be on this line. And on the other direction, for example, we have square root of 2, which is here. And so not only if we add two numbers in this number field, we just add them as vectors, but also we have component-wise multiplication. Okay, that's what the embeddings tells us. The embeddings preserve addition and multiplication. So if we represent each one of each axis, then we got component-wise addition and component-wise multiplication. Okay. Also, we might notice that this lattice has some symmetries. Of course, multiplication by -1 is a symmetry, but we also have the conjugation to be a symmetry. So basically, if we exchange the y and the x-axis, we still obtain the same lattice. And this is basically related to the fact that we have a Galois automorphism that sends one embedding to the other. Okay. So now let's take a little bit look at the geometry. So there are those elements that I've put in blue on those blue lines that are somehow orthogonals. What do I mean by orthogonals? I mean that if you multiply by those elements, you don't get any distortion. So for example, if you multiply by 2, you get a scaling, but it does not distort anything. But it's also the case if you multiply by square root of 2, where you're going to, basically multiplying by square root of 2 means that you're going to turn by 45 degrees and scale by square root of 2. So those elements don't have distortion, but for... I'm sorry, yes, I might have been confused. Yes. But other elements, if you multiply by other elements, then you get a distortion. For example, if you multiply by this guy, well, you multiply in this direction you're going to end up multiplying the x direction a lot, and on the contrary, decreasing the y direction. Okay? So those elements out of the blue line have some form of distortion, and the further away from the blue line, the worse the distortion is. So now, in red, I've put the units. So the units are elements that have algebraic norm, 1, and those are the elements that are invertible. Okay, and because of this equation having algebraic norm 1, well, we get that the units lies onto this red hyperbola. And finally, I've drawn the other isonorm curves. So why I've drawn them? Well, because it means essentially that when you multiply by a unit, you stay on this same curve. So what is the problem that we're trying to solve when we look at this drawing? Well, basically, we're going to be given a generator of some ideal, maybe this one or another one, and we're trying to multiply it by a unit so that it gets the less possible distortion. So we're trying to find a unit that will take it as close as possible to those blue lines. We want our element to be as orthogonal as we can. So now I'm going to represent those embeddings on the left and the logarithmic embedding on the right. So now those orthogonal elements, this blue line, it has been sent to this blue line over there. And now the units, so this hyperbola, it has been sent to something that is orthogonal to. Sorry, the left-hand side is the canonical embeddings, the Minkowski embeddings. And on the right side, it's a log embedding. So basically, a point here is sent to the logarithm of its coordinate. So we take logarithm, we take the logarithm of the absolute value of each coordinate, and we send the point from one side to the other. So now it means that basically when you're moving along those hyperboles, you're just moving in those directions in the logarithmic embedding. Okay? So now we have a better visualization of the question of distortion versus scaling. Okay, the distortion is going to be measured by how far from the origin you are on this axis, whereas the scaling part of a generator is going to be measured on this axis. Okay, and so as I told you before, if we consider those blue points in this set with the addition, then we obtain a submonoid of R2 because it's a logarithm of the multiplicative monoid of the ring. Okay, and as I said, if we restrict this monoid to the units, then we get a group, and in particular we get a lattice, which is always going to be orthogonal to this direction 1, 1, 1. So here, this set, the blue points that lie on this line, this is the lattice lambda. Okay? And as I told you before, oh, yes, this one. Then because this is a monoid, okay, and this is basically the base group of this monoid, then if we start with a point, we can always move up and down by this monoid. So it means that whenever we have a point on the line, where we're going to get a whole copy of this original lattice on this line. So basically, each of those lines, each of the blue points of those lines, they are finitely many shifted copies of this original log unit lattice. It can happen that these lines are empty, but it can happen that you get multiple of them. And so this is what we were targeting for. So now we want to, given a generator, we want to use units to reduce it, to make it as small as possible. So as I told you, we wanted to move along those orange lines to get it as close as possible to being orthogonal. And if we look at this in the logarithmic embedding, well, it just means that we want to bring them back to a fundamental domain of this log unit lattice. So this is what I've drawn here. This is the fundamental domain. And it means that whatever point we have, by using those lattice points, we can always bring it back to this original fundamental domain. And then we can map back this fundamental domain here, and we obtain those cones. So it means that by using unit, we can always get back to this cone. Okay? So, of course, there are many possible choices of fundamental domain. In dimension 1, there is a very natural one, which is basically half of the interval defined by a fundamental point in your lattice. But in more dimension, you will have more choice of a natural fundamental domain. And if you change this fundamental domain, of course, you're changing basically the cone you're reducing to in the original Minkowski embedding. All right. So as I told you, we have many choices in which fundamental domain we choose to reduce to, and here we're thinking algorithmically. We're not just thinking mathematically. What are the possible fundamental domain? We want a fundamental domain that we can efficiently reduce to. So we want essentially an algorithm on the log embedding that brings us back into this wide beam of light. So in one dimension, it's pretty trivial. In more dimension, what you need, of course, is a basis of the lattice and an algorithm to do so. So there are a lot of very fancy algorithms to get very good fundamental domains, the smallest, I mean, the one that fits in the smallest sphere. Here we're going to use a very, very basic algorithm to reduce modulo a lattice. It's called the Rundhoff algorithm. The reason we do so is that despite it's not necessarily the best one, it's actually much easier to analyze. So this algorithm is called Rundhoff because basically we just round off the coordinate in the using the basis of our lattice. So we multiply by the inverse of the basis, we round, and we multiply again. And if we try to use this algorithm as a decoding algorithm, that is, we're given a point that we know is a lattice point, V. So we're given T. We know it's a lattice point V plus some error E. The question is, if we apply this algorithm, is this algorithm going to give us back the original error and the original lattice point that we have? And when we use this very simple algorithm, it's very easy to characterize when this algorithm is correct. This algorithm is going to be correct if the error, when you take its scalar product with any of those dual vectors, if this scalar product is small, meaning between -1/2 and 1. Okay, so I'll indulge myself with more pictures on how this algorithm works. So basically, it maps back the problem to a very simple lattice, a square lattice by multiplying all the target and the lattice by the inverse or the dual basis. Then it rounds its coordinate, and then it sends back the solution to the original lattice. All right. So now that we have all those tools, what is our goal, and what are we going to do? So there is a general strategy, a four-core strategy to try to solve this problem. So you try to construct a basis of that unit log lattice. So in general, it's not an easy task. In general, it's a task that for arbitrary number field, it's a task that can take sub-exponential time. But we're lucky because the case that we're trying to attack, well, there exists already basis of that lattice, or maybe not exactly a basis. Maybe sometimes it's a basis of a sublattice of it of a small index. We hope, and this basis is given by what are called the cyclotomic units. Okay. So they're given by this formula. So this is actually the basis that we're going to use. And it turns out that this basis is actually a very good basis. And this is why experimentally this problem was easy. But what we want to do here is not only verify that it is good, we want to prove that it is good, which would explain a little more why this works. Oh, sorry. So the first one is Dan Bernstein, and the second one is Campbell, Grove, and Shepard, as in this other paper. So I don't know if it's something. Yeah, it's something that goes way back. But I mean, for bringing attention to this strategy in crypto is certainly due to them. All right. So this is what we do in our paper. We try basically to prove that this approach works. And to do so, we estimate the length of those dual vectors. And the amusing thing is that, well, to do so, we will actually use tools from analytical number theory. So this was for us a quite surprising appearance of this theory in based crypto. Maybe for Albrecht, it's something that's actually quite natural. And then the second part of it is to also prove, so that, remember we wanted to prove that the scalar product of this E with the dual vector of this basis was small. So we basically want to prove that this is small, and we want to prove that this is small, and we'll obtain the correctness of the decoding algorithm. All right, so this is our two technical contributions. Proving the basis is good, and also proving that the error is not too bad. All right, so we can move to our first objective. So studying the geometry of the cyclotomic units. So again, now we fix our number field. We fix it to the m's cyclotomic field for m power of a prime. And in that case, we can easily construct units as follow. So we're going to take zj to be 1 minus zeta to the j. So by itself, it's not exactly a unit, but if you take two of them and you divide them, you actually get a unit. Okay? And if you want an independent set of units, you can obtain such an independent set of units by all dividing them by the first one. So you take bj to be zj over z1, and then you get an independent set of units. And this is classically known as the group of cyclotomic units, which is a bit awkward because it's not necessarily the whole groups of units of the cyclotomic number field, but it's how it's called. So as it's said here on the footnotes, this does not necessarily generate the whole group, but the index is believed to be small. So that's the first simplification we're going to do. We're going to assume that this set of units actually generate the whole group of cyclotomic units. And this is conjectured to be the case for powers of 2. So this is known as Weber class number problem. And more generally, we know that the index is kind of solved, which is enough for our purpose. We conjecture that the index is kind of small, which is enough for our purpose. The second simplification that we're going to do is that the bj are not exactly very convenient to compute with, but the zj are much easier. And it can easily be proved that those two matrices, the one generated by the log of the zj and the one generated by the bj, are actually kind of close to each other. So for this talk, we'll just study the dual matrix of Z rather than the dual matrix of B. All right, so how does this matrix look like? Well, we first have to explicit the embeddings. So we have phi over 2 pairs of complex embeddings that are conjugate to each other. So we choose a root of unity in C, and we basically send zeta to all the roots, to all the primitive roots of unity that we have. And if we do so and we draw our matrix, this is the kind of drawing that we get. So here, the darker means the largest value. And obviously, we've been a bit naive when we did this, because it seems that there is some kind of structure. Again, we see hyperbolas, and this is a picture of the matrix Z. So the matrix that is given by the logarithm of those units. But here, I've been indexing everything quite naively. I've been using the additive or the natural indexing of that set. Yes, sorry. Yes, sorry. So this matrix is, so if I just take the first column of it, so the first column of it is a logarithmic embedding of Z1, of Z1, of Z2, sorry, because it started. So that's going to be the log of, I have the explicit formula on the next slide, I think. Yes, so that's, the matrix is, each index ij is supposed to be omega of, log of 1 minus omega to the ij. Pardon? Omega is a complex root, is a primitive complex root of the unity. Yes, so basically here we've done something a bit naive, which is to choose the indexing of our matrix without taking the fact that there is a group structure actually on those units. Darks mill large and whites mill, yeah, I think so. I mean, we shouldn't really care, but the values, the structure is more interesting. Yes, I think it's all value. I mean, the point that I want to make here is actually we should order this matrix differently. We should use multiplicative indexing. We should index this matrix using the powers of 3, because 3 generates this whole group. Okay? Because we're using the primitive roots of unity, we're only going to use I that are in this group. Okay? So we really want to index this matrix according to the group structure, rather than to just use the natural or the naive indexing. It's 1, 3, etc. So when we use this multiplicative indexing, we suddenly realize that this matrix has a lot of structure. It is a circulant matrix, all right? And if we didn't have this structure, it would be very, very hard to try to study its dual basis. But because it has this structure, there is a very easy way to compute the size of the dual vector. So, okay, we have this matrix. So, as I told you, each coordinate, so each vector of that matrix was the log embedding of one of those units. So those are the units. Okay, 1 minus, well, those are not exactly units. I told you I cheated a little bit and didn't put exactly the units. But here we're studying, so the G's embedding of 1 minus zeta to the I, okay? And sigma j sends zeta to omega j. Okay, that's the G's embedding. We're sending zeta to the G's root of unity in the complex group. So, and as I told you, this matrix, because of this, well, it is circulant for the multiplicative group ij. So if if the product ij remains constant, then the values on that matrix are going to be equal. And yes, yes, yes. So yes, it's yes, yes. You're right. Yeah, I'm sorry this is confusing. The whole point of this slide was to show the circulant structure, but yeah, I should have definitely added the scale. The scale. Pardon? Yes, yes, yes. You're taking the log of cosine, yes, which yes, yes, and the other one as well, because then you multiply you multiply by a constant number inside the cosine, so suddenly the periodicity increases. But but actually this representation is, if you want to study this matrix and its geometric property, of course we see better this structure with this representation. But if we want to actually compute stuff on this matrix, changing the indexing is actually the cute trick that makes everything works nicely. For what? Yes, yes, definitely. I should get one. Okay, so how are we going to use this fact that the matrix is circulant? Well, if a matrix is circulant, basically we know how to diagonalize it. We know how to compute its eigenvalues. So if it's circulant for a certain group G, then its eigenvalues are essentially going to be given by the characters associated with G. So G hat, you can see this as a dual of the group. Okay? Huh? Oh, so if you remember, our program is to compute the size of the dual vectors of this matrix. Yes, yes, yes. I want the size of the vector of the inverse of this matrix. Yes, yes. And that's a nice thing about circulant matrices, is that you can compute easily the eigenvalues, and from the eigenvalues then you can compute the inverse eigenvalues, and then you can compute the inverse norm. So that's what I'm giving in this fact, okay? Oh, because it's what huh? It's what tells you how good of the basis it is. So okay, I can go back. Okay, it's this fact on the Rundorf algorithm. So this algorithm is going to be correct if the error that you're trying to repair is has a small scalar product with all those guys. So you basically want to prove that those guys are small and that those guys are small, and then you ensure that they lie in this interval. Okay? Hmm? Well, because now I'm studying, so I have this matrix Z, and I want to compute the size of the inverse of this matrix. Okay? So of course I could just compute it for a fixed dimension. I can just take the matrix, fit it into Sage, and compute its inverse. But here I'm trying to understand what happened asymptotically.
One is near explained, and what you care about this is another one. Round that's all you care about, you can prove it. The coding radius, the radius in which you can find it in the picture is GD2 by the square of the longest vector in the two. What we're trying to do here is figure out how far we can do from the code to find the nearest. And this is simply a function of the longest vector in the two. The goal is simply to the dual. The goal basically is
Okay, I'm sorry. Yes, it's. I mean, if you apply a reduction algorithm to this basis, very strange things happen. Yes, if you apply HKZ, you get a worse basis than you're starting with. So that's. Huh? They're not perfectly orthogonal, but they're very close to orthogonal. But HKZ makes them worse. So that's quite peculiar. But yes. So let's go back to our computation. We want to compute the eigenvalues, because then from the eigenvalues we can compute the norm of the dual vectors, of the reciprocal vectors. All right. And those characters, so here they're defined over this multiplicative group G, but we can easily extend this definition so that they're defined over all the integers. So that's called a Dirichlet character, and we can define them over all the integers by simply reducing to their class modulo m, and we set this character to be 0 if the value a is not congruent to, sorry, if it's not an invertible element in D. All right, so this is the function we want to compute. We want to compute lambda equals the sum of the chi bar of A times log of 1 minus omega A. That looks nasty. I actually didn't really want to do that when I saw it, but then we can just stop here. We can just fit this formula into a computer algebra program, and then we can compute those values up to very large dimension, because this is a very simple formula. You can compute it very efficiently, and then you can verify that Rondorf is correct up to very, very large dimension. So why shouldn't we stop here? Well, because it's more fun to just actually try to get a proof. So maybe this equation looks nasty, but you know, it appeared somehow naturally. We found a lot of structure, and it just popped out. So maybe mathematicians actually know what to do with this. And this is the case. So if you look in the book on Washington on the cyclotomic number field, you'll find that the same kind of formula appears, not to compute the quality of the basis, but just the volume of this lattice. So this is somehow a weaker information, but this is the same kind of information. And it's not surprising that the same kind of computation can actually solve our problem as well. Pardon? Oh, you've ruined my talk. Yeah, that's what's gonna happen. So basically, you take this formula, you do some Taylor series expansion, and then you end up with something that looks even worse. So now you have a double sum. But yeah, and one of the sum is infinite. You're summing for all the integers, okay? You play again with this formula, and then you first apply a magic trick of Gauss. Actually, this second sum that you have here, well, maybe the result is going to be something that turns around, but the norm, the magnitude of this sum is fixed. So basically, the sum, the size of this sum is given to you basically by the size of the group. So yes, so now we can slightly simplify our formula, and then the L function becomes obvious. So what we want to compute again, well, we don't want to compute them exactly. We want to bound them, but it's this lambda xc which is given by this formula. So we have a fixed term here that we can now safely ignore, and now what we're trying to deal with is this term. So here we have a character of chi, so that's something that you know, turns over and over on the unit circle, but maybe you know, it turns in a weird way, but it's cyclic, and it's periodic, sorry, and then you're dividing by k. So what really happens, it's not even directly obvious that this sum converge. I mean, if we didn't add a character on top, this would diverge, but it's not what we worry about. We don't, actually, we want this sum to be not too small. Okay, so you can play a lot with this formula before you realize that the solution is already known since about a century. So yes, so that, you rewrite this, and actually this sum, the second term, you can recognize a Dirichlet L series, and it was known since quite a while that those sums are bounded from above and from below by they're quite strongly bounded. We know them up to a logarithmic factor, and even if you drop some strong assumption like Riemann hypothesis or generalized Riemann hypothesis, you can even bound them stronger than this, and you can get log n or something. Yes, that's Lando. I'm sorry. Yes, but the original article. Yes, the original article is in German, so maybe you don't want to follow the reference. I mean, huh? Is it German? Okay. Yes, that's what it said. Yeah, we get log n instead of log n. Yes. But that also explains why it behave even better in practice than in theory, because this is just a syntactical result. So why should it work so early in small dimension? Or maybe this is part of this. No, for this result we don't need the Riemann hypothesis, but we can get a stronger one with the Riemann. Pardon? I didn't catch it. Okay, I'm admittedly playing with force beyond my reach. Pardon? M is the conductor of the number field. Pardon? M is the prime powers and it grows. All right, let's admit this is true. yes, no, but I mean. So this is how I understood the theorem I read. If you admit that this is a proper interpretation of it, then this basically gives the result that we wanted, because then you can plug everything back together and you can obtain a bound on the norm of those reciprocal vectors. All right, so we get that their square norm is less than 1 over m times a log factor that we can safely ignore. What's more important is the polynomial factor. So this leaves us with the second task, measuring how big the error that we want to correct is. So we want to prove that the g that we're gonna have the error is gonna be log of g, and this is what we want to recover. Yes, sorry.
basically the same as any short as you might get through. They would have something on the CA. I mean,
No, you get there should be a log somewhere because the regulator is
maybe they were talking. Imagine those B, those
yes.
vectors for example.
Well, you still have to take you still have to take account for the volume.
For the given net.
Yes. Yes. Oh, okay. So just knowing the length of the B and reducing the length of the dual vectors that were orthogonal. No, you would get a log. You would just get one inverse log actually. I've got to double check that. Yes, but yes. So one interpretation of this this theorem, if all the steps are actually right, is that is that basically yes, this basis is very close to orthogonal, meaning that when you take its dual, you're basically gonna get the inverse length of the original. All right, so let's move to the third point. So we have proved, so sorry, we started, so we had a 3-point program. The first was to construct a basis, but that was already done for us. Then we wanted to prove that this basis is good. So we proved it. And then we need to prove that the error we're trying to recover is small enough. So that's our last step. I'm going to be quite quick on this step, but essentially, so we have to assume something on the distribution of what we want to prove is short. So let's say that when we take the embeddings of this generator that was generated as a secret key, let's assume that when it takes its embedding, all those embeddings are independently identical distribution following the distribution. So first thing that we notice is that when we take the log embedding, really the scaling of this distribution doesn't really matter. Okay, if we multiply by, if we get a distribution, for example, that's twice larger, then what happens is that we just shift our distribution in the log embedding. Okay, that's this simple equation. If we go back to the pictures, it means that when we scale up a distribution, so maybe we have a distribution that's maybe spherically symmetric, and here we get a blob, then we take its log. Well, if we scale up this distribution is just going to shift on this axis. And because this axis is orthogonal to the lattice, it's not going to affect how our lattice decoding algorithm is going to perform. So basically, it means that we can scale up and down the distribution. It's not going to change much. So this means that basically we can assume that the average of log D is whatever we want, because we can shift it around and around. So we're going to assume that this log of D distribution is actually centered in 0. And we're going to take this error vector that's the logarithm of this distribution. All right? And what we obtain is that each coordinate of this random vector are independent centered, and they have a fixed variance V, assuming log of D actually has a variance, that its square is summable. Let's assume this for a while. Then remember that what we were trying to prove is that this guy was less than 1/2, and we know that B is less asymptotically than 1 over the dimension. So if we take the scalar product, on average, sorry, not on average, but the variance that we will get for this scalar product is going to be the norm of that vector multiplied by the variance of the coordinates of this vector B. No, it's not. Well, Yeah, because E is log of G. Okay, so that's part of what. I mean, there is an assumption on the distribution here, but then when we instantiate it with a distribution we use in crypto, then it's going to happen. And yes, that's one of the points. If it were uniform modulo the log lattice, then we would get basically an arbitrary CVP problem. We wouldn't get a bounded distance decoding problem. Also, one other point is that if instead we were to use a distribution, as you said, that would be uniform in the log embedding, then it would mean that even if we obtain the best generator in this class, well, then it wouldn't be good enough for cryptography. Actually, Chris is going to talk about that. In general, that does not exist for an arbitrary principal ideal. They do not necessarily exist a very good generator of it. So I think Chris is going to detail that. Okay, but my point is that once we have this variance in this B, well, this variance is fixed. So when the dimension increases, because this guy is in 1/m, well, then we can use Markov inequality and say that this scalar product is going to be less than 1/2 with a small enough probability. All right. So unfortunately, that's not good enough to conclude because we've just proved that one of those scalar products is less than 1/2 when we need all of them to be less than 1/2 at the same time. And the probability that we prove this is too small to just repeat this argument n times and take a union bar. So we need the argument a bit more, actually quite more clever than this to make it work. But yeah, I'm going to jump to the conclusion. Essentially, to make this work simultaneously on all the eyes, then we need to study in more detail this distribution and its tail. And this can be done using the theory of sub-exponential random variables. Versioning. Yes. So all those arguments comes from also early 20th century from Bernstein, no? Those sub-exponential random variables? Yes. Huh? Yes. Yes. Okay. So that's the conclusion. So that if we take G to be a continuous normal distribution, so here it's a bit weird because we're supposed to be in the ring of integers, so how can we take it continuous? So that's just a proxy to obtain the final result. We tensor it with the reals and take something continuous, and then in that case we get the result that we wanted. That is, if you take E to be log of G for G following that distribution, then with very high probability you will get that the algorithm will decode it properly. And as a corollary, you can also get it for discrete normal distribution. So in particular, we're going to be able to apply this to the cryptographic instances of interest. You lose a little bit on the probability of success. Here you only had negligible probability of failure. Here you get to a probability of failure that is 1 over a polynomial. So it means that maybe some of the keys are not going to be that easy to break, but the algorithm is going to succeed on most of the keys. It's probably just a proof artifact. Because I didn't really properly define those distribution, I think. Yes, I think that's the reason I put quote around it. I think the exact theorem in the paper has to be significantly longer to be precise. All right. So yes, I'm bringing to another slide. So this is a Shintani domain. So when you have a fundamental domain of in the log embedding, and when you push it back to to the Minkowski embedding, we obtain what's called a Shintini domain, and apparently some mathematicians have quite some interest in drawing them. So here is one, and I also want to thank a few people for guiding us in this research.
Paul was actually somebody who supported in SATI.
Pardon?
Paul Dunn was somebody who supported this year in SATI.
Oh, okay. Wonderful, wonderful. I found this a few days ago, and I like, as you see, I like drawing pictures, and I was happy to see that. But some mathematicians also like to represent those stuff graphically.
Is it the point?
It's supposed to be a cone. I don't know exactly how he represents it, but yeah, I cannot read this picture yet, but I'll spend more time on it. So, actually, René Schuf I made the same comment first, and we discussed, and then he was convinced that it was actually okay. Sorry, I didn't catch. So the steroid statement is wrong, or maybe I should write for large enough m, and then it would be right. Mm-hmm. Pardon? Okay. Yeah, but then it's not. The question is this a theorem or it's not? So it's not. Yes, m is the power of p, but p might be 2. Okay, so and then if we restrict, it's very unlikely. Okay, and if we restrict it to the, because the characters that we have, we need. I mean, the characters that we. Okay, as a theorem, it might be wrong, but if we restrict it to the characters that we actually need here, do we have a chance that it becomes right? If they're not quadratic characters, then it's right. Is it? The issue is with quadratic character. Is that it? Okay. 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 Yes, we only use the lower bound. Yes, that's the one that's problematic. Yes.
So what we
He also mentioned issues with quadratic characters. Yes, yes, yes. But okay, maybe we should. I don't think we need quadratic characters. I think all the characters that we use are not quadratic. Yes, we need. Yes, yes. Thank you. Yes, yes. It lacks an assumption. We agree.
This would be simply German. Then you wouldn't understand.
I mean, the attack is easy to mount in Sage. No, I mean not the PIP part. It's like what we tried out. Well, first we have also computed explicitly those values, but also yes, if you generate. So what you do is you generate a random generator, and then you multiply by random units, and you try to see if you actually recover this original generator. Because we're not able to mount the PIP attack because it's still sub-exponential. This is quite costly and it's quite painful to implement. But yeah, we've been able to test the attack in some.
Others do that too.
Yes. Did they mount the PIP attack? You know?
No, signal.
Uh-huh. A short one. Yes, yes. This is there is a lot of happy coincidence that make it all works. A slightly different number field. Yes. So it all depends on the geometric structure of the group of units. So I mean, if you here we have a basis that's more orthogonal than what you would expect from anything random. It's unnormally orthogonal. I have no idea how this would work for other. But it's also hard to speak of a generic number field for this because to make it useful for cryptography, we need a good Z basis of that number field. Otherwise, we cannot do anything with it. So we already have to select number fields that have a particular geometry, and maybe having a good geometry, having a good basis, a good Z basis to generate the number field, the ring of integer itself. Maybe this implies something on the units. I mean, here I have no idea. Oh yes, yes, yes. You can. Yes, you can. You don't have to go to the ring of integers. You can use any. So overall, one issue with this approach is that once you fixed once you fix the number field, then the logarithmic unit lattice is fixed. So it's not like breaking the crypto system would require reducing a new basis of something that kind of re-randomize each time. It means that then we have fixed something that that has some algebraic structure, and then suddenly someone might come up with a very good basis for some reason. So I think it's a dangerous game. Yeah, that's true. That's true. I mean, there is a way to build a factory here. That's what I mean. You can do a lot of initial efforts to then solve the problem cheaper than your opponents. So that's usually not a very good situation for crypto systems.